Hey friends, welcome to the YouTube channel all about electronics. In the previous video, we have seen that how the PN junction diode can be operated in the forward as well as the reverse bias condition. And we have seen that in the forward bias condition, when the applied voltage is more than this threshold voltage or the barrier potential of this PN junction diode, then the current starts flowing from the P side to the N side. On the other end, in the reverse bias condition, there is hardly any flow of current from P side to the N side, but a small amount of reverse saturation current flows from the N side to the P side. And we had seen that this current flows due to the minority charge carriers. And then we had seen that even if we increase this reverse bias voltage, then also there is hardly any change in this reverse saturation current. But there is a maximum limit on the voltage which can be applied in this reverse bias condition. And if we apply this voltage beyond this limit, then suddenly lot of current starts flowing in this reverse direction. So this region of operation of the diode is known as the breakdown region of operation, and the effect due to which it occurs is known as the avalanche effect. So let us understand what exactly happens in this effect and why suddenly current shoots up after this breakdown voltage. Now we know that in the reverse bias condition, the current which we are getting is due to the minority charge carriers. So in the reverse bias, as we increase the applied reverse voltage, the width of the depletion region will increase. And due to that, the immobile ions in this depletion region will also increase. So because of the increase in this immobile ions, the electric field in the depletion region will become stronger. And due to this stronger electric field, now the minority charge carriers which are in the vicinity to this depletion region will get accelerated, and now they can move more quickly through this depletion region. And while moving, these free charge carriers can collide with these silicon atoms. But once the applied voltage reaches the breakdown voltage, then the kinetic energy which is gained by this charge carrier will be such that they can knock off the bound or the valence electron of these silicon atoms. So if we see the same thing at the crystal level, then the accelerated electron may collide with the silicon atom, and when it has enough kinetic energy, then it can knock out a bound charge or the valence charge of this atom. So after the collision, instead of one electron, now we have two free electrons. And under the influence of the electric field, now these two electrons can collide with the two more atoms and they can knock out the two more electrons. Similarly, now these four electrons will again collide with the four more atoms and they can knock out the four more electrons. So due to this collision, the number of free charge carriers in the depletion region will increase drastically. And due to the increase in this charge carrier, we will see a sudden jump in the reverse saturation current. So this effect is known as the avalanche breakdown effect, and the voltage after which it occurs is known as the breakdown voltage. So far as we have seen, this avalanche breakdown effect is caused by the impact ionization, meaning that the high energy charged particle can knock out the bound electron from the silicon atom, and in this way it creates the electron hole pair. So for the normal diode, this region of operation should be avoided, because when the applied voltage is more than this breakdown voltage, then the diode starts conducting in the reverse direction also. Moreover that, if there is no current limiting resistor in series with this diode, then due to the very large current or very high power dissipation, this diode may get damaged. So for the normal diode, this region of operation should be avoided. But there are some diodes which are meant to be used in this breakdown region, and this diode is known as the Zener diode. But in the Zener diode, the breakdown mechanism is different from the avalanche effect, and this breakdown mechanism is known as the Zener breakdown effect. So now let us understand what exactly happens in this Zener breakdown effect. So unlike the normal diode, the P and N type regions of the Zener diodes are heavily doped, meaning that the number of impurity atoms in this P and N region will be more, and due to that the number of free charge carriers in both regions will be more. So here, instead of denoting these two regions by P and N, here these two regions are denoted by the symbol P plus and N plus. So basically it represents that these two regions are heavily doped. So now due to this heavy doping, the width of the depletion region will be much narrower compared to the normal diode, because now when the electron diffuses from N side to the P side, then it will get recombined very much near to the junction itself. And moreover that, due to this heavy doping, this small depletion region will now have a more number of immobile ions compared to the normal diode. So due to this, now the built-in electric field inside this depletion region will be much stronger. And when this diode is reverse bias, then the external electric field will also get added with this built-in electric field. And due to that, now the electric field in this depletion region will become very strong. And at one particular voltage, it will become so strong that it can knock out the bound electrons of this silicon atom. So due to this very strong electric field, many charge carriers are generated, and due to the very narrow depletion region, they can tunnel through it and they can reach the other side of the depletion region. So in this way, due to the very high electric field, many charge carriers are generated in this depletion region, and suddenly a lot of current starts flowing in the reverse direction. So this effect is known as the Zener breakdown effect, and the voltage at which this Zener effect starts is known as the Zener voltage. But this Zener effect is seen at the lower breakdown voltages. Now from the graph, if you observe, even if we increase the applied voltage beyond the Zener voltage, then the voltage across the diode will almost remains constant, and only the current through the diode will increase. So because of this property, the Zener diode is used as a voltage regulator in many applications. And the commercially available Zener diodes can have a Zener voltage from 2 volt to even 200 of volts. But for the Zener diodes whose breakdown voltage is less than 4 volt, the Zener effect is predominant. On the other end, for the Zener diodes where the breakdown voltage is more than 6 volt, the avalanche effect is predominant. And for the breakdown voltages between this 4 volt and 6 volt, both effects are usually seen. But irrespective of the breakdown mechanism, all the diodes which are used as a voltage regulator are categorized as Zener diode. So now before ending this video, let us also see the effect of temperature on these two breakdown mechanisms. So for the diodes where the Zener breakdown effect is predominant, the temperature coefficient of breakdown voltage is negative, meaning that as the temperature increases, the breakdown voltage will reduce. On the other end, in case of a diodes where the avalanche effect is the predominant, the temperature coefficient of breakdown voltage is positive, meaning that as the temperature increases, the breakdown voltage will increase. So now let us also see the reason behind these two effects. So in case of a Zener effect, the additional charge carriers are generated due to the strong electric field. But as the temperature increases, the more and more number of electron-hole pair will get generated. So due to that, now we require a less electric field to generate these additional charge carriers. Or in other words, we can say that the required breakdown voltage will reduce. On the other end, in case of an avalanche breakdown effect, the additional charge carriers are generated due to the impact ionization. Or in other words, we can say that it is generated due to the collision of the charge carrier with the silicon atoms. So as the temperature increases, the silicon atom starts vibrating. And due to this vibration, the mean free path of the collision will reduce. Or we can say that the time required between the two collision will reduce. So due to that, now the electrons will not be able to gain the sufficient kinetic energy. And due to that, now they will require a more electric field. Or in other words, we can say that they require the more external voltage. So we can say that in case of an avalanche breakdown effect, as the temperature increases, the breakdown voltage will also increase. So this is all about the avalanche and the Zener breakdown effect. And in summary, here is a list of differences between the avalanche and the Zener breakdown effect. So I hope in this video you understood the two types of breakdown mechanism which is commonly seen in the PN junction diode. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.